Good everyone, welcome back to Medics Mike's YouTube channel. So today we are going to be talking about different major calculations that appear in most examination questions. So please, if you have not subscribed to this YouTube channel, please hit the subscribe button and the notification button so that you'll be notified when I post a new educating video like this. Thank you. So like I said earlier, we are going to be treating basic or let's say major calculation questions that appear in most examination, be it UTME, post-UTME, WAEC and so on. So that includes empirical formula, molecular formula, easy steps to finding oxidation number, and calculating water of crystallization in hydrated compound. That is a little bit complex and gives students a lot of difficulty in the exam or tending to waste their time. But here we're going to give you easy steps in which you can arrive at your quick answer. Let's take a ride. So let's start by knowing what empirical formula and molecular formulas are. Now, an empirical formula is a formula that involves the simplest composition of a compound, or as the definition says, it expresses the composition of the compound in its simplest whole number ratio of atoms of different elements in the compound. Whereas our molecular formula is also called true formula. It contains the actual composition of the constituent elements in the compound. Now what do I mean? For example, we have a compound which is NO2, and over here we have N2O4. You can see that these two compounds are like in terms of simple ratio, meaning that this can be represented as the empirical formula, which is EF, and this is the molecular formula, because if you divide this constituent element by 2, it will give you the same ratio as 1:2 as you have here. Another example you can use is CH2O. Now this can be referred to as the simplest formula of your simple sugar, and this is an empirical formula. You can call this an empirical formula, which in turn can represent a molecular formula, which is C6H12O6, and this will be representing our molecular formula. Now with this, I want us to establish a common relationship between our empirical formula and our molecular formula. To be empirical formula in brackets N equals to molecular formula. Also put this in brackets, where N here is representing the simple whole number ratio in which the atoms of your EF, which is empirical formula, is being multiplied to give you your molecular formula. Now if you check the example we used here, our N becomes 6, and once we put 6 here, you see that 6 times C, which is carbon, will give us 6, and 6 times H will give us 12, because there's already 2 subscript there going with hydrogen, and also 6 times oxygen, 1 atom of oxygen will give us 6. We'll get to know how to solve this relationship better, but just keep this formula in your head as we go further to learn how to solve our empirical formula. So we have some laid out rules over here which we'll be using to solve our empirical formula. Now these 3 major rules are the rules you need to know to solve your formulas on empirical, any question you come across at all. So as we get ourselves familiarized with these rules, we are going to be solving a question along so we can assimilate better. So this is the question: what is the empirical formula of an oxide containing 72% of manganese by mass? So the first step to take is to write out your constituent elements and make sure they are up to 100% since it was given in percentage, and that takes us back to row 1. And row 1 said finding the mole of the constituent element using mass. So we have to find the moles of the constituent element, and if you have seen my video on stoichiometry, which I will leave the description link below, you will know that to find your mole it's mass over molar mass, as easy as that. So we are going to be using our mass, and our mass can also be given to us in percentage. But we should also note that the total composition of atom when given in percentage must be equal to 100, because in some question they will not give you the total mass of all the elements. They expect you to know that the whole composition must be equal to 100 for you to know that you have to subtract the total that was given to you in the question, and the answer you get from 100 will be the remaining mass. What do I mean? This question, we were given 72% of manganese, and manganese oxide means the compound contains manganese and oxygen, which we have already written here, and it contains manganese in 72%, and this percentage can also act as our mass in gram. But we are not given the percentage of oxygen. That is where that rule comes in, where we have to subtract 100, where we have to subtract 72 from 100. So 72 minus 100 is equal to 28. So our mass, or rather percentage of oxygen, will be 28. Now remember, rule 1 is saying that we should find our mole, and we can take our percentage in grams. So our percentage can also act as the masses. So we have to find our mole, and we all know that mole is equal to what? Mass over molar mass. Mass over molar mass. So our molar mass that was given to us in the question was respectively for manganese 55, and for oxygen it is 16. So that having established, we just have to punch that in our calculator, and it will give us 1.31, and over here 1.75. Now that takes us to our rule 2, and rule 2 says the mole obtained from the rule 1 is mostly in decimals, we have seen. Now to convert them to whole number, we have to divide through by the simplest mole. Now between 1.31 and 1.75, which is the simplest mole? Of course 1.31. So we have to divide both sides by the simplest mole, which is 1.31, and over here we'll still divide by 1.31. And when we punch that in our calculator, we'll be getting 1 over here. 1.31 divided by 1.31 give us 1. While 1.75 divided by 1.31 will give us 1.34. Now, this brings us to root 3, because we can't take this as our answer because they are not yet in simple ratio. Now, what does root 3 say? Root 3 say if in case you still don't get a simple whole number after step 2, just as we are at that point now, we should multiply through by a factor that will make it possible for the whole number to be obtained. So what we need is a factor, a number that we can multiply 1 with and 1.34 to get a whole number respectively. Now in examination condition, at this point I will advise to start multiplying from 2. Now if you multiply by 2, you don't still get a simple whole number ratio, you go to 3 and so on. And for this case it is 3. 1, so you multiply 1 times 3, you'll be getting 3 for sure. So here will be equals to 3 for manganese, and you'll be multiplying 1.34 by 3 too, and you'll be getting 4. So at the end, the compound you'll be getting is Mn3. This is Mn3O4. That will be your final answer, as easy as that. Alright guys, test 2, we have a different pattern of question which says on combustion of 0.065 gram of an organic compound which contains carbon, hydrogen and nitrogen, it only yielded 0.0146 gram of carbon dioxide CO2 and 0.089 gram of water H2O. What is the empirical formula? Now this is different from the one we solved previously, but not entirely different. The only thing we have to do first to get to that stage where we follow our rules is to find the masses, respective masses of these atoms in the organic compound. Now what we need to know here first of all is that carbon plus hydrogen plus nitrogen is equal to 0.0065 gram. 0065 gram. So we have to obtain the respective masses of carbon, nitrogen, and oxygen, and all together will sum up to 0.0065 gram. Now, how do we get the mass of carbon? So first of all, we'll be looking for the mass of carbon. Now, to get the mass of carbon, we have to compare the mass of carbon to the mass of CO2. Now, by simple comparison, what we are going to be doing here is CO2 to carbon. Now, what's the molar mass of CO2? Molar mass of CO2, just quickly, is 12 plus 16 plus 16, which is equal to 44. While the molar mass of atom is 12. So we are just going to be putting this value beneath them here. So you have 44 gram per mole here, and you have 12 gram per mole. Now, by simple comparison, we'll be saying if 44 gram per mole of CO2 was able to give us 12 gram of carbon, or 12 gram per mole of carbon, how many gram of carbon will 0.0146 gram of CO2 give us? So here becomes X. The 0.0146 gram is gotten from the question at this place where we are giving 0.0146 gram of CO2 as one of the products, and we'll be using this CO2 to get our carbon, and using the hydrogen, using the product of water, which is 0.0089 gram, to get the gram of our hydrogen. So first of all, let's focus on carbon. So if you punch this on your calculator, it will be X equals to 0.0146 gram times 12 divided by 44. Remember, what we are doing here is that we are getting the respective masses of our constituent elements, so we can find our empirical formula. And when you punch that in your calculator, you'll be getting 0.00398 gram. So that's being established. We just write it down here. The mass of carbon is 0.00398 gram. Now up next, we'll be looking for the mass of hydrogen through water by the same means in which we got the mass of carbon. The same simple comparison, we will use that method to get our mass of hydrogen. So we'll be comparing water, H2, to hydrogen gas, H2. So here, mass of H2 is 18, which is 2 plus 16 will be 18. So this is 18 compared to 2 gram per mole of H2. So we'll be saying if 18 gram per mole can give us 2 gram per mole of H2, what gram per mole will 0.0089 gram of water give us? So here becomes X, and X becomes 2 times 0.0089 gram divided by 18. So after punching that in your calculator, you get 0.00099 gram of H2. So here we just come off hydrogen. So here we just come and write 0.00099 gram. So next we'll be looking for our mass of nitrogen, and our mass of nitrogen can be gotten by simple addition and subtraction. What do I mean? I mean that when you add carbon plus hydrogen plus nitrogen, it gives us a total of the compound, which is 0.0065 gram. So what we are going to do is to write down our respective masses that we have calculated. So for carbon it will be 0.00398 gram, plus for hydrogen it is 0.00099 gram, plus N will be equal to our total mass over here, which is 0.0065 gram. So it's a little bit tiny. So what we're doing next is N will be equal to 0.0065 gram subtracted from the sum of 0.00398 plus 0.0099, which is when we add the respective masses of carbon and hydrogen, we'll be getting 0.00497. So it will be this subtracted from this will give us our mass of nitrogen, and punching that again we'll get 0.00153 gram. So this is our answer, and you can come and write it here, 0.00153 gram. Normally in combustion reaction, rather for you to see nitrogen, you might see oxygen, so you will still get the mass of oxygen by the same means, by adding the mass of carbon that we got from CO2 and mass of hydrogen that we got from H2O, then you subtract it from the total mass of the organic compound, you get the mass of your remaining compound. So since we have our respective masses here, what we have to do next is to look for our empirical formula. Following our rule 1, it says we should divide each masses with their molar mass to find their respective mole. So this will definitely be carbon. The mass of carbon is 12, and here the mass of hydrogen is 1, and over here the mass of nitrogen is 14. So we divided them through by their molar mass, and the mole of carbon will be 0.00033. Mole of hydrogen remains the same because it is dividing by 1, so here it becomes 99. So mass of nitrogen becomes 0.00011. So according to our rule 2 says we should divide with the smallest mole, and the smallest mole we have here is the mole of nitrogen, which is 0.0011. So we are going to be dividing through by 0.0011. So after dividing through, we'll be getting here as 3, while here will be 9, and here will be 1. So at the end, we are having our empirical formula to be equal to C3H9N1. 1 is appearing as a subscript 3. So I'm just going to recap how we got our answer. We had to first find the respective masses of carbon and nitrogen using simple comparison between CO2 and water H2O respectively, and then we summed up our value, which we calculated for both carbon atom and hydrogen atom, and we subtracted it from our total mass, which is 0.0065 gram of the organic compound that went into reaction, and then we got our mass of nitrogen over here. Then we had to impute all the masses over here and divide them by their molar mass to get their mole, and we had to divide through by the simplest mole and get our respective empirical formula. As simple as that. If you don't understand, just go through the video again and try to solve more questions like this so you can familiarize yourself with it. So we are just going to take one question which involves molecular formula, then we'll go into oxidation number. We have a question which says, what is the molecular formula of cryolite if it contains 32.85% of sodium, 12.85% of aluminium, and 54.30% of fluorine by mass? The relative molar mass of the compound is 210. So we have to look for the molecular formula and not the empirical formula. But to get your molecular formula, you have to first find your empirical formula, which by now should be very easy. We'll just write down our respective atom, which is sodium, aluminium, and fluorine. So for sodium, we have 32.85%. For aluminium, we have 12.85%. And for fluorine, we have 54.30%. Next, we'll find the mole by dividing by their molar mass, which this is 23, this is 27, and this is 19. So when you divide through, you get 1.42 mole for sodium, 0.475 mole for aluminium, and 2.847 for fluorine. So what we have to do next is to divide by the lowest masses, by the lowest mole, So this will be divided by 0.475. Same thing over here, 0.475. Same thing over here, 0.475. And when you punch that in your calculator, your answer will be 3, 1, and 6 respectively for sodium, aluminium, and fluorine. So our empirical formula becomes Na3 Al1 then F6. This becomes our empirical formula. But hope you remember the question did not tell us to look for empirical formula, but rather it told us to look for our molecular formula. And at the beginning of this video, we established the relationship between empirical and molecular formula. We said that empirical formula in brackets n, where n is a common factor number which multiplies our empirical formula to give us our molecular formula, is equals to molecular formula in brackets. So remember that this is the empirical formula we calculated. So we are just going to put it in brackets as 3Na plus Al plus 6F close bracket n is equals to our molecular formula, which was given to us in the question as 210. So going through that, it will be 3 times 23 plus 27 plus 6 times 19. And when you multiply and sum them up, you get 210 in bracket n is equal to 210. So I'm just going to wipe this off. So n becomes 210 divided by 210 equal to, so since we have our n now, we can actually get our molecular formula, which in this case is the same thing as the empirical formula. That is to tell you that not all compounds have different empirical and molecular formula. Mind you, n is not always 1. N can be 2, 3, 4, and so on and so forth. But for this question, we have our empirical formula as Na3. We have fluorine 6. All in brackets 1 will be equals to the molecular formula. So this times by 1 will remain the same value. So we can say that the molecular formula will be the same equivalent as the empirical formula. Alright everyone, the next calculation we have on our list is how to solve oxidation number using various simple steps. Now, oxidation number is a very important aspect of chemistry that is tested in most examination conditions, and they are very easy to solve if you understand the concept and how to solve more difficult questions when you see them. Now, solving more difficult questions means you have to start from the fundamentals, that is from these simple rules. And the first rule you need to note is that free elements in an uncombined state has oxidation number of 0. For example, we have sulfur. This oxidation number of X8 is equal to 0 because why? It is an uncombined state atom, an uncombined state element in its free state. It is equal to 0. You can take another example as free sodium is equal to 0, free aluminium is equal to 0, and so on and so forth. Free phosphorus is equal to 0. So whether the atom is polyatomic or monoatomic or diatomic, it is sure equals to 0 as far as it is in a free uncombined state. Now, the next rule is for ions consisting of only one atom, they have oxidation number equal to the charge on the atom. So for this, you must make sure that the ion is equal to 1. That is just one ion, not a polyatomic ion. It must be a monoatomic ion. For example, we have sodium ion. So if you are being asked for the oxidation number of sodium ion here, it will be +1 because why? It is carrying the +1 charge on it. So this will be +1 according to the rule. What about calcium ion? So calcium ion, oxidation number is what? +2 because it is carrying the +2 charge. What about chlorine ion? Chlorine ion is what? -1 because it is carrying the -1 charge. Now the next rule is that for oxygen in most compound, it is -2. Oxygen in most compound, it is -2. Let's take for example SO2. The oxidation number of oxygen there will be what? -2. But for peroxides, an example of peroxide is hydrogen peroxide, and hydrogen peroxide is represented by the molecular formula H2O2. So for all peroxides, the oxidation number of oxygen is -1, while for superoxides, the oxidation number of oxygen is -half. So that should be established now, and we should know how to go about our calculations later in this video. Now for the next rule, we have oxidation number of hydrogen is +1. Yes, oxidation number of hydrogen is +1. Even hydrogen ion is represented like this when it has lost 1 electron. So the oxidation number is what? +1. And in most compounds, except those of binary metals, oxygen comes at +1 oxidation number state. Now, an example of a binary metal is NaH. Yes, this is an hydride, which is sodium hydride, and the oxidation number of hydrogen here will be -1. So that's the only exception to hydrogen. For our next rule, it is saying in a neutral molecule, the sum of the oxidation number of all the atoms must be equal to 0. What do I mean? For example, you have H2SO4, which is an acid. The oxidation number of the sum of all these elements is equal to 0. So from this, you can start finding their individual elements or their individual oxidation number rather. And you should note that for a compound to be stable, to be equal to 0, the number of cations must be equal to the number of anion. Let's take for example this compound now. Hydrogen, if you calculate hydrogen, hydrogen is +2. It's +1, but since it is 2 molecules there of hydrogen, or rather 2 atoms, it is +2, while sulfur is +6. So +2 + 6 is +8. And oxygen normally, according to our rule 2, or rather rule 3, is -2. So 4 times -2 would be what? -8. So you can see +8 minus 8 is equal to 0. So this is just a proof that for every neutral compound, the oxidation number is equal to 0. Why? There is an equal amount of anion and there is an equal amount of cation in that compound. Now, still on the last rule, which says in a polyatomic ion, the sum of the oxidation number of all elements in the ion is equal to the charge of the ion. What do I mean? For example, you have NH4+, which is ammonium ion. The sum up of the charges in this compound is equal to +1, because that's the exact charge that it is carrying. This rule is similar to our rule 2, which says for ions consisting of only one atom, it has the oxidation number equals to the charge of the ion. But rather, in this last rule, it is referring to a polyatomic ion. So the sum of all charges of the elements or of the individual atoms in this ion, in this polyatomic ion, is equal to the charge that it is carrying. So for ammonium ion, it is +1. Now, what's the proof? The oxidation number of nitrogen in this compound, in this polyatomic compound, -3. And the oxidation number of hydrogen is +1. So +1 times 4 is +. So -1 plus 4 is equal to +1. So you can see that confirms that it is same thing as the amount of charge that the polyatomic ion is carrying. Up next, we are going to be establishing more on our understanding by the following questions. So number 1, first of all, the question says we should calculate the oxidation number of the underlined element. So the elements that has been underlined, the oxidation number will be calculated for. For number 1 over here, number 1, we have Ca, open bracket, ClO3, close bracket, 2. Now, first of all, the first thing to do is to bring out these elements in their respective numbers. So calcium is 1, chlorine should be 2 because of the subscript outside, and oxygen should be 6 because 2 times 3 is 6. So 6. Oh. So the next thing to do is to write out the oxidation number. And here's one trick you can use to know oxidation numbers for calculation purpose. For group 1 elements, their oxidation number is mostly equals to +1. For group 2 elements, their oxidation number is equals to +2. That is for the alkali earth metal. For the alkali metal, group 1 is +1. While for the halogens, all halogens, which is group 7 elements, the oxidation number is always -1. Example of halogens, we have the chlorine, we have fluorine, we have iodine, bromine, and we have astatine, and so on. So the oxidation number of all these elements in group 7 is -1. So there are some various tricks that you can use to know oxidation number for calculation purposes. So let's go back to our question. First of all, remember that for a compound, the total oxidation number of that compound is equal to 0 because there's the same number of anion and cation in that compound. So for calcium is in group 2, the oxidation number is +2 plus Cl. So Cl is the constituent that we are looking for. So we can turn it to X. So 2X. So plus 6 brackets -2. The oxidation number of oxygen is -2, except in peroxide or superoxide. And the compound we have here is not a peroxide, neither is it a superoxide. So we'll go with -2. The next thing to do is to open the brackets. So this will be +2 plus 2x. So this will be 6 times -2, which is -2. 12 is equal to 0. And making x subject of the formula, we'll be having 2x is equals to, once plus 2 goes to the other side, becomes minus 2. And once minus 12 goes to the other side, becomes plus 12. So this will be 2x is equal to plus 10. And dividing by 2, divided by the coefficient of x, this will divide by 2, and this will also divide by 2. So x ends up to be plus 5. So the oxidation number of chlorine in that compound is plus 5. For number 2, we have SO4 2 minus. Now this is a polyatomic ion, and for polyatomic ion, their charges is equal to their oxidation number of the total polyatomic ion is equal to the charge it is carrying. So it is fair enough for us to say SO4 is equal to minus 2. Now we are looking for the oxidation number of sulfur. Fair enough, we can turn that to S. So S is equal to, X plus 4 open bracket minus 2 is equal to minus 2. Hope you understand. The oxidation number of oxygen is minus 2. So when you multiply that and open the bracket, to be X plus, or rather, because it is minus, so it will be X minus 8 is equal to minus 2. So when you take 8 to the other side, it becomes plus 8. So this becomes plus 8, and X becomes plus 6. So the oxidation number of sulfur in SO4 2 minus is equal to plus 6. Now number 3 is a very easy one, which is NgO, magnesium oxide, is equal to 0 because it's a compound. So we go Mg becomes X because it's the compound we are looking for, Mg minus 2. So the oxidation number of oxygen there will be minus 2 is equal to 0. So X becomes what? Plus 2 when it goes to the other side. So as simple as that, the oxidation number of manganese, or rather magnesium, is equal to plus 2. Number 4, we are looking for the oxidation number of phosphorus in H3PO4. So everything here will be equal to 0. Oxidation number of hydrogen is plus 1. So plus 1 times 3 is 3. Or let's just write that very broad so we can understand. So it is 3H plus X, which is P that we are looking for over here, plus 4O is equal to 0. So this will be 3 plus 1. 3 times plus 1 is plus 3 plus X. So this will be 4 times what? Minus 2 is equal to 0. So plus 3 plus X plus 3 plus X minus 8 is equal to 0. So X becomes plus 8 minus 3, because once you are moving these figures the other side, their sign is also changing. So this will be plus 5. So the oxidation number of phosphorus in H3PO4 is equals to plus 5. Number 5 is a pretty easy one, very easy. If you paid attention very well to our rules, you should know that a molecule on its own, or an element in an uncombined state, the oxidation number is equal to 0. As simple as that. So for number 6, we have chromium oxide, Cr2O7, all equal to 0. Law of neutrality, that is, there must be equal number of cation and anion in the reaction, making it all equal to 0. So here we have the constituent element that we are looking for, plus 7O is equal to 0. And remember, the oxidation number of oxygen is minus 2. So we'll be having 2x plus bracket minus 2 times 7 is equal to 7. we'll then be having 2x minus 14 is equal to 0. Hence, we'll make x subject of the formula to be x is equal to plus 14 divided by 2. So x is equal to plus 7. Next on our list is how to calculate water of crystallization, and this is a question that most examiners like to test a lot. It can be a little bit complex to solve, but I've given a very quick formula in which you will be able to solve it very quickly. I'll be giving that formula very soon, but before then, get to understand what water of crystallization actually means. So water of crystallization is a definite amount of water some substances combine with when they form salts from their aqueous solution. Now, normally, how is salt formed? A salt is formed from a neutralization reaction, right? Where an acid reacts with a base to give us what? Salt and water. And when these salts combine with water, some salts combine with water in a definite amount, and that amount is what we call water of crystallization. Now, water of crystallization has some functions in the salt. It gives it color, it gives the salt color, and gives the salt its shape. That is why you actually see them referring to some salts as crystalline, because any salt that is referred to as a crystalline salt is a salt that has water of crystallization or has the tendency of forming water of crystallization when it comes in contact with H2O. Now, there is a very important thing to know. There's a difference between anhydrous salts and crystalline salts. They are the opposite of each other. When a salt loses water of crystallization, it will lose its shape and it will lose its color, and hence it is called an anhydrous salt. There are some salts that does not form water of crystallization at all. They are called anhydrous salts. So I'm just going to give some examples of anhydrous salts. So we have example of anhydrous salt. We'll be having KMnO4. This is an example of an anhydrous salt. And our common salt NaCl is also an anhydrous salt. And KNO3 is also an anhydrous salt, and so on. This is but just a few examples of anhydrous salt. Now, example of crystalline salt, example of salt with water of crystallization include copper 2 triazonitrate 5 trihydrate. The trihydrate there already tells us that it is an hydrated salt and it has water of crystallization in it. An example of such salt is the one I just mentioned now, and the molecular formula is CuNO3.3H2O. So indeed it is a trihydrate, and this compound is copper 2 triazonitrate 5 trihydrate. Now let me just give another example. We have sodium triazocarbonate 4 decahydrate. Sodium triazocarbonate 4 decahydrates. So deca means 10. So you can see that this salt has water of crystallization. Now our major aim here is to know how to calculate the amount, the definite amount of water of crystallization. That is this 10 and 3. So you might be given a question that consists of an hydrated or an anhydrous salt, but you will not be told the amount of water of crystallization that is there. So you'll be asked to calculate it. So when you are asked to do that, there is a very easy formula that you can use, and this formula is this. So guys, this is the formula to solve any question relating to water of crystallization. So N here, to understand better, N is equals to the amount of molecule of the water of crystallization that we asked to find. So WOC means water of crystallization, while M means molar mass. So we have to calculate the molar mass of the compound that we are asked to find the water of crystallization. While H is simply the gram, the mass actually, mass in gram of hydrated salts. So H means hydrated salts. You'll be given this in your question. While A means anhydrous salts. A means mass of anhydrous salts. Mass of anhydrous salt. So that H minus A is just the mass of hydrated salt minus the mass of anhydrous salt. Same thing with the A under here, also means mass of anhydrous salt. The reason why number 18 is being used is because the molar mass of H2O is equal to 18. 2 plus 16 is equal to 18. So that's why 18 is being used there. So take a while, write down this formula and let it stick better as we go into solving our question with it. The next question is saying on heating 5 grams of hydrated salt of barium, the weight gave 4.26 grams of anhydrous salt with molecular weight of 208 grams. Now we are being asked to find the number of molecules of crystallization in the hydrated salt. So first of all, we write down our formula, which is N is equals to M bracket H minus A close bracket divided by 18A. Now you can take a pause to this video and try if you can impute these figures in and get your answer straight up. So if you have done that, let's do it together. Now N is equals to M. Now we are given the molecular weight, which is same thing as our molar mass, M. So it is 208. Molar mass is 208 bracket hydrated salt is 5 grams minus anhydrous salt is 4.26 grams close bracket divided by 18, and I've explained why we are using 18 is because of the mass of water times anhydrous salt again 2 point. So when we subtract and multiply, we'll be having 208 open bracket 0.74 divided by 18 times 4.26 will give us 76.68, and when we punch all that together we'll be getting 2. So our N is equal to 2. And what that means is that anytime barium goes into a reaction to form a salt in an aqueous solution, it is definite that the water of crystallization will be equal to 2. And this water of crystallization, as I earlier explained, gives the color and shape to all crystalline salts. 40 grams of a hydrate of calcium sulfate lost 8.368 grams of water on heating. What is the formula of the hydrate? This is the same thing as saying that what is the number of molecule of water of crystallization. What do I mean? This compound in an hydrated form, it will be CaSO4.XH2O. So this is the X we are looking for. Same thing as the previous question, but this one we are not given the molar mass, so we have to calculate the molar mass by ourselves. Remember our formula, N is equals to M open bracket H minus A over 18A. So writing our parameters at our M is equal to, we are going to be calculating our molar mass from CaSO4, So this will be 40 plus 32 plus 4 times 16. So when you punch all that together in your calculator, your answer will be 136 grams per mole. So that's our answer. So we already know our M to be 136 grams per mole. Write it down over here, 136 grams per mole. Now our H was given to us in the question as our hydrated salt, which is 40 grams, and our A is equal to 40 grams minus 8.368 grams. Now you should understand that at the early stage of this topic, we said that an hydrated salt is a salt that has water of crystallization, while an anhydrous salt is a salt that has lost its water of crystallization. So if you read the question very well, 40 grams of a hydrate of calcium sulfate lost 8.386. So 8.386 is not the mass of the anhydrous salt. Rather, it is the water of crystallization that has been lost from the hydrated salt, and the mass that is left will be our anhydrous salt. Hope you understand. If you don't understand, keep your questions at the comment section. I will attend to it very fast. So 40 minus 8.386 gram is equal to 31.632 gram. So what we have to do next is to impute these values in our formula. So this is 40 minus 31.632 all together over 18 times 31.632. So you can just punch this once in your calculator and your answer will be 1.99, which is approximately 2. So our answer is 2. Note that water of crystallization is always or most times equal to an whole number, or after calculating it will give you a value that you can easily approximate, like 1.99 is easily approximated to 2. So after this, we can say the formula of the hydrate to be calcium sulfate dot 2H2O. So this will be in the option and you have to easily pick your answer. So guys, we have come to the end of this video. It takes a lot to set up this video, so please like, subscribe, share, leave a comment in the comment section. God bless you as you do so. Thank you.